What I want to do today is continue talking about routing games, talking about their equilibria, when and in what senses are they close to an optimal solution. The first two results I want to discuss today, I kind of want to interpret in the context of a case study. The case study is in the strategy, when you're managing a communication network, of what's called over-provisioning. So the routing model we've been talking about is sort of general enough to cut across a few different domains. It originates from transportation networks back in the 50s, or even sort of implicitly before that. But one big advantage in communication networks, which is not so true in transportation networks, is it's relatively easy and cheap to add capacity to communication networks. If you tell your urban planners to go add 4 more lanes to Highway 101, it's not so simple. So a popular strategy for people who actually do manage communication networks is to install extra capacity. So more capacity than is needed. And all I mean by this is that if you look at the network, at any typical moment in time, it's going to be not fully utilized. In fact, possibly quite far from fully utilized. So a lot of the capacity will just be sitting there unused. And if you look at communication networks out there today, that is in fact a property of them. They're not even close to fully utilized, generally speaking. So there's no, I don't know of a definitive reference on the over-provisioning strategy to give you, but if you Google it, you get lots of research papers, you get discussion forums where network managers are discussing whether or not to do this, and if so, by how much, and so on. So it's really, like I said, something that's used quite commonly. So why would you want more capacity than you really need? So one reason is you want to make sure, if demand suddenly grows for your network, you have sort of enough capacity there to absorb it. But I want to focus on performance reasons that you might want to install extra capacity, and these have been observed empirically. And so I'm going to mention 2 things, and we'll have theorems that correspond directly to these 2 empirical observations. So empirically, the network just functions better for whatever performance measure you want, packet drops, delay of traffic, whatever. The more capacity you have, the better the performance of the network. And 2, when people think about sort of a related point, when people are sort of asking the question, what should we do with our network to make sure the performance is reasonable? For example, to guarantee, certain latency for our end users, when you download a web page or what have you. It's often thought that it's cheaper to just add extra capacity, make the network, bigger and therefore function better, as opposed to having some kind of smart control, possibly in software. So doing something like guiding the performance of the network with the current capacity toward optimality. So it's not to be cheaper than somehow being smart and enforcing, what in networking they call QoS, or quality of service. So this would be just, guaranteeing some kind of end-to-end delay, for example. And one way you might do that would be some kind of admission control procedure whereby you actually are able to refuse entrance of some traffic to the network in order to keep the congestion down. So there's not consensus on this topic, but there's a sizable camp that believes, rather than be smart about managing the traffic in your network, just make sure there's more than enough capacity to hold it. Okay? And so again, so these are just empirical phenomena, and I want to show you 2 mathematical results which corroborate this real-world experience. All right, so the first result is actually just going to be an instantiation of what I already told you on Monday. We went over a very general theorem on Monday. So I'm just going to instantiate in a particular way. That'll correspond to point number 1, that the more you're over-provisioned, the better the network functions. So we'll have a sense in which the more over-provisioned, the price of energy will get closer to 1. And then we'll prove a new theorem making this precise. All right, so on Monday, we worked with arbitrary sets of cost functions. And so to illustrate this point, I want to now instantiate cost functions to look like this. So every edge is going to have a capacity. It's called U sub E. And the cost or delay function, it'll be, there'll be some basic propagation delay with 0 traffic. And then as it gets more and more congested, of course, the delay goes up. And it goes up very sharply as you get to the asymptote. Okay, so qualitatively, that's what the cost functions are going to look like. So we're going to consider a selfish routing network, just like we were talking about on Monday, where every edge cost function has the form, well, if you're over capacity, then it's infinity. So basically, you can't go over capacity. And if you're under capacity, then it grows as the reciprocal of the capacity remaining. Okay, so 1 over the capacity minus the amount of traffic on it. At least a few of you, I hope, have encountered functions like this previously. This is the standard delay function for what's called an MM1 queue, a queue with Poisson arrivals and exponentially distributed service rates. If you take a textbook on networking and you just start reading from page 1, this will be the first delay function that you find in a networking textbook. Okay. All right. So we want to have a mathematical statement that says the more the network is over provisioned, the better it will function. Okay. So here's what over provision is going to mean for us. And I'm going to parameterize it. So alpha over provisioned. And by this I mean that the maximum link utilization in the network at equilibrium is 1 minus alpha. Okay? So meaning, if I look at the amount of traffic using any given edge, of course it's got to be less than the capacity, because otherwise we'd have infinite cost. But actually, it's even at most 1 minus alpha times the capacity. Okay? So for all edges at equilibrium. Okay, so one of the most basic network measurement tools is you just look at link utilization. So what I'm saying here is just inspect, zoom in on each of the links in your network, look at the link utilization. If all of the links utilization is at most 1 minus alpha, okay, so maybe alpha is 0.1, so that'll be 90% link utilization, then we call it alpha over provisioned. The more the alpha, the more it's over provisioned, the less it's utilized. Okay? All right. So I'm going to skip a calculation. But it turns out, what we did on Monday was we basically gave an algorithm for computing the price of anarchy, the worst case price of anarchy, for any set of cost functions. Right? So what did we prove? We said, well, it doesn't matter what your network is, how big and complicated it is. Whatever the price of anarchy is, it's no worse than one of these 2-node 2-link networks. Okay, you always realize worst case price of anarchy on 2-node 2-link networks. So we could take that abstract set C of cost functions to be these MM1 delay functions with the additional restriction that flow never uses them more than 1 minus alpha times the capacity. Then there's going to be some trivial network with cost functions like that that realizes the worst case price of anarchy, and we can just compute it in that small trivial example. Okay, so I'm going to skip the details of that and just give you the bottom line of what you get when you do the calculation. So it follows from what we said yesterday that in any alpha over provision network, again, no matter what the topology is, just as long as the equilibrium obeys this condition, so you get an exact formula, which is also tight, so this can be realized, as we know even in very simple networks, that the price of anarchy is bounded above by the average of 1 and the square root of 1 over alpha. So let's just sort of get a feel for this, okay? So, what's intuitively, hopefully, what you'd expect intuitively is, as you make a network massively over-provisioned, then in some sense these cost functions are like essentially constant, right? So, if you have so much capacity that basically you're never going to fill up a link at all, it's almost like you have constant cost functions, and you'd expect traffic to be on shortest paths. Everybody would be happy. It would basically be optimal. So you would expect that as alpha approaches 1, okay, as the link utilization approaches 0%, you'd expect a price of anarchy of 1, and you see that. Okay, plug in alpha equals 1, then you get 1. If you let alpha go to 0 and you make no guarantee on how far away you are for capacity, well, then you're going to be near this asymptote, and it's like a crazy steep cost function. And we know from Monday that even in simple networks with crazy steep cost functions, the price of anarchy can be arbitrarily large. So we're not also surprised to see that as we take alpha going down to 0, as the max link utilization approaches 100%, this blows up to infinity. So what's cool is we have this exact expression that we can evaluate with interesting values of alpha, that might correspond to something in practice. So for example, alpha equal 0.1. Okay, so if you plug in alpha equal 0.1, this is like 10 under the square root, so this is a little bit more than 3. So the average here is going to be a little bit more than 2. Okay, so a special case says max link utilization at most 90%. And again, in reality, many link utilizations are far less than 90%. But as long as everything's at most 90%, this says the price of anarchy is bounded by something just a little bit bigger than 2. Okay? So that's a sense in which, from what we already learned on Monday, we see how the self-shrouding theory corroborates this real-world experience. Okay? That networks perform better the more they're over-provisioned. So that's the first sort of vignette about network over-provisioning. Let's move on to this. Let's see if we can have something which allows us to compare the benefits of adding capacity versus the benefits of being smart about the traffic management. All right, so I just mentioned this, but let me mention it again, which is we know that if you make no assumptions about cost functions at all, you can't say anything about the price of anarchy. It can be arbitrarily large. And we know that just from the nonlinear version of Pigu's example. Okay? So on Monday, we argued that as d goes to infinity, the optimal solution can split 1 minus epsilon epsilon, with epsilon going to 0, so the opt goes to 0. Whereas the equilibrium is 1, no matter what d is, so that ratio blows up to infinity as d goes to infinity. Okay? So the point being that even in very simple self-shrouding networks, the price of anarchy is unbounded in general. So the main thing we did on Monday is we made assumptions about, and that we just did in the last application, is we made assumptions about the cost functions. And we said as long as they're not too steep, then in fact the price of anarchy is bounded. It's near 1. But what if we actually want to say something about networks with arbitrary cost functions, so cost functions of the form x to the d? What could we do? Well, one thing you could do is you could make extra assumptions, not on the cost functions, but about maybe, say, the traffic matrix and about the network topology. And there's been some work in the systems community. There's a SIGCOMM paper from about 10 years ago that does exactly that. It says if you look at quote-unquote internet-like topologies, even for arbitrary cost functions, the price of anarchy is pretty small. So that's a totally legitimate way to proceed. We're going to do something different here with an eye toward this comparison of adding capacity versus smart traffic management. So what we're going to do is we're going to take an arbitrary network, including, say, the nonlinear Pigu's example, and we're going to compare the equilibrium to a weaker benchmark, a weaker version of opt. And the trick is, in our comparison, we're going to force the optimal flow to send additional traffic. Okay? So, and we can already see how this might work in the nonlinear Pigu's example. So if the equilibrium flow has to route 1 unit of traffic, as usual, it will all go on top. So the equilibrium costs 1. But what if now I let you route optimally, but I force you to route 2 units of traffic in that top network? What are you going to do with it? If you only have 1 unit of traffic, you can split it 1 minus epsilon and epsilon. But now if you have to route a second unit of traffic through, you're sort of stuck. Okay? Either you can route it on the bottom link, which is always expensive, or you can route it on the top link, but then it's going to get congested and you lose all your benefits. So if you have to route 2 units of traffic, there's nothing better you can do than putting 1 minus epsilon on top and 1 plus epsilon on the bottom. And your cost then in routing 2 units of traffic is going to be more than 1, which is what the equilibrium pays routing only 1 unit of traffic. Okay? So we're going to seek some kind of generalization of that observation. And to further connect this to the previous point, I'm going to ask you on this exercise set to prove that comparing to an optimal solution that routes additional traffic is mathematically exactly the same thing as comparing to an optimal solution with the same amount of traffic, but in a slower network, with in some sense worse cost functions. Okay? And so the interpretation here, so now same amount of traffic with both the equilibrium and the optimal, but these different networks, a slower one and a faster one. What this says, what we're going to prove, will imply that an equilibrium in a faster network is even better than an optimal solution in the original network. Okay? And in fact, if you have these MM1 delay functions, it has a particularly nice interpretation. It says if you double the capacity and use equilibrium routing, that's at least as good as if you used optimal routing in the original network. Okay? So this is a precise way of saying the performance will be better if you don't try to manage traffic and you just add capacity, you double capacity, versus not adding capacity and routing optimally, doing the best you can in the original network. Okay? So that's what this theorem is going to imply. So here's the formal statement. This is an old result with my PhD advisor, Eva Tardos. And so the real benefit here is that now we're going to make no assumptions on the cost functions at all, other than the baseline assumptions, non-negative, non-decreasing, continuous. So in particular, the theorem will apply to networks like this. So the cost of an equilibrium flow with R units of traffic is going to be bounded above by the cost of an optimal flow with 2R units of traffic. Okay? So the generalization of what we observed in the nonlinear Piggers example, where forcing opt to route 2 units forces its cost to be above 1, the equilibrium cost. Okay? So this is the formal mathematical statement, and I've tried to sort of give you a narrative in the sense in which it formalizes this philosophy that adding capacity, meaning using a faster network, does better, has smaller cost than not adding capacity and being smart about routing traffic. Okay. So up next is the proof of this. Any questions? So no, that's more what's going on in this equivalent version. So it can be rephrased as such, and that's exactly what the exercise asks you to go through. But in the theorem that I'm about to prove, there really is fundamentally twice as much traffic in the optimal network. Okay? But again, I mean, your interpretation is correct, but it takes an additional change of variable, basically, which is what this exercise asks you to do. Other questions? Okay. Yeah, but it's optimal, right? So if it's just equilibrium flow, yeah. So there's two different moving parts here, right? So I basically give you full control over the network, but I make you route twice as much. Obviously, the first thing makes your life easier, the second makes your life harder, and it's totally unclear who's going to win the tug of war. Yeah.
Should that be forced to use faster network?
Yeah, no. No, we want to make opt weaker, right? So opt should get the slower network. Or if you prefer, you know, we get the faster network, but we're just going to be very dumb about our routing. Okay. Okay. So proof's not too hard. So we've got our equilibrium flow. It routes only R units. Like last time, it's going to be F. And like last time, F star will be the opt flow. And that routes twice as much traffic, 2R units. Okay, and I'm again going to assume that everybody starts from the same source and is going to the same destination. And it's again true, see exercise set 6, that this extends to multiple sources and multiple destinations with essentially the same proof. Okay? But it's simpler to see what's going on with one source and one destination. So recall the definition of an equilibrium flow. Okay? Any flow in use is shorter than any other, any path in use by an equilibrium flow has to be as short as any other path with respect to the current traffic. So in particular, all paths in use have exactly the same travel time. Okay? And like on Monday, I'm going to call that capital L. And what I'm going to do here is really kind of conceptually exactly the same as part one of the proof that I gave you last time. So what were we doing there? So the hard part about trying to get a grip on the optimal's cost is that not only is the traffic pattern different than the equilibrium, but once you mix up the traffic pattern, the costs themselves are different. So how do I compare these two different flows, which are measured with respect to totally different cost functions? But we had this nice idea on Monday, which was that, well, if only we froze the costs at the equilibrium amounts, then because the equilibrium sort of routes everything on shortest paths, with those fictitious frozen costs, any other flow is only going to be worse. And here we're routing twice as much traffic, so it's actually going to be twice as bad. Okay? So we're going to just do that exact same trick here. So we're going to freeze the costs at the equilibrium values to give us a grip, to give us some kind of handle on a version of the optimal's cost. Okay? So the equilibrium flow, total travel time or cost. So let me just write it in the path version. So the amount of flow in a path times the cost of that path. And the path cost is L for any path that it actually uses. And then, of course, it's a flow that routes R units of traffic. So these values sum to R. So just like last time, we get an R times L, amount of traffic times the common cost of all traffic. That's the equilibrium cost. And if we use the fictitious equilibrium cost to lower bound the optimal flow value, we can do that as well, just like last time. So if I look at the optimal flow, routing 2R units, and I don't measure its cost with respect to the proper costs, meaning the costs with respect to F star, but rather I freeze them at the equilibrium values, well, we know that these are all at least L, because the equilibrium routes stuff on shortest paths. And for this flow F star, we've forced it to route 2R units of traffic. So we know this sums to 2R for F star. Okay? So that's what we get. We get that if we use the wrong costs, okay, so we're going to have to pay the piper later, but for now, if we use the wrong costs, we actually get a fantastic lower bound on the optimal flow. Remember, that's what we want to do. We want to say the optimal flow is at least as expensive as the equilibrium flow. Right now, we're saying it's twice as expensive, but of course, we're cheating. We're not using the cost with respect to F star, we're using the other ones. But it does reduce the proof to showing that the overestimate, potentially, introduced by using the wrong costs is at most R times L. So remember, this is the equilibrium cost. We want to say that the optimal flow is at least this. This erroneous version of the optimal cost is at least 2RL. So if we're off by only RL, then we're done. Okay, then, in fact, the real optimal cost is at least RL, and that's what we're trying to prove. So in other words, to finish, it's enough to show. Now remember, last time we had two ways of writing costs. We could either sum up over the paths or sum up over the edges. So I'm going to now write these exact same quantities, but as the sum over edges instead, so don't get confused by that. So we want to prove that right, so this is the cost of F. This is what we want to lower bound. So I've written it in the edge form. Let me do it this way. This is exactly the same as this, just written in the edge form instead of in the path form. So this we just argued is at least 2 times RL. So this is our fictitious lower bound on the optimal cost. And then this is just the cost of the equilibrium flow written in the edge form. And as we observed, this is exactly R times L. Okay? So we have not proved this inequality. This is the inequality we're about to prove. So what you're supposed to observe right now is that if we successfully prove this inequality, then we're done. Okay? What are we trying to prove? We're trying to prove that the optimal flow, F, is at least as expensive as the equilibrium, optimal flow F star is at least as expensive as the equilibrium flow F. So here we have cost of F star. If we successfully prove this, then we get it's at least 2 times RL minus R times L, i.e. R times L, which is indeed the equilibrium cost. Okay? So if we prove this inequality, then we've proved the theorem. Agreed? Okay, so we're going to prove this inequality. We're going to do it edge by edge, separately for each edge. Okay? Let's say we'll show for each edge E. So let's just look at the summands for a particular edge E. I'm going to rearrange them here, but it'll be the same thing. So I'm just going to take the summand from this one and move it over here and move that one over there. Okay? And flip the right and left hand sides. So what you get when you do that is the following. Okay. So if we prove this inequality, then we apply it just term by term and we get the desired inequality from which we have the theorem. Okay? So we've just done some content-free rearranging. The theorem boils down to understanding this. Okay? And in some sense, here's what we're trying to do here. So we observe that if we cheated and froze the cost at the equilibrium levels, we really easily got this super strong lower bound on the optimal cost. We proved that it leaves double the equilibrium cost. So fundamentally what we're trying to show is that our overestimate in our cheating is at most once times the equilibrium cost, because then our residual lower bound is still once times the equilibrium cost, and we're good to go. Okay? So that's what this is saying. It says look at a given edge. Okay? This is the difference between the costs frozen at the equilibrium amounts, which was our cheat. This is what we actually should have been using. So this is our error in cost per unit of flow. This is the amount of flow that we're incurring that error for, the amount of flow that the optimal flow actually routes on it. And we're saying that that's at most the equilibrium cost. Okay? So summing over all of the edges, this is just the overall error we make by using the wrong costs. And this is saying that total error is at most once the equilibrium cost, R times L. Okay? Okay, but now in any case, we just need to draw a quick picture and we'll see this is true. Right? Okay. So here's an easy case. What if, so F and F star could be any non-negative real numbers. What if F star is bigger than F on this edge? What can you say? So cost functions are non-decreasing, as always. So if F star is bigger, then this cost is bigger, which means the left-hand side of this is actually non-positive. So that's clearly true. Okay? So easy case, F star E at least FE. Okay? Left-hand side is non-positive. So the merely slightly less easy case, suppose the amount of optimal flow on E is less than the equilibrium flow, F star E less than FE. And consider the following picture. So this is going to be the flow on E and the cost of E. So this is going to be some kind of cost function. Okay. And now let's look at F star E. So again, the x-axis is amount of flow. The y-axis is the cost. Okay? So here's two candidate flow amounts, F star E and FE. And F star E is further to the left. So let's look at what all these quantities are. So the right-hand side, the equilibrium flow amount, so that's F, so width F sub E, height cost of F sub E. Okay, so the right-hand side is this rectangle. Right? That's our upper bound on the error on this edge. The left-hand side, well, it's F star E, so it's going to have width F star E. And then it's the difference between the cost in the cost function evaluated at F star E versus FE. So the height is going to be this. Okay. Oops. Okay, so this is the left-hand side. And then the entire shaded rectangle is the right-hand side. Okay? And so in general, the width of the left-hand side rectangle will be smaller because F star E is less than FE. And in general, the height of the left-hand side rectangle will be less than that of the right-hand side one, just because the difference in costs is bounded by the difference in costs between 0 and F sub E. Okay? So that's it. So that verifies this inequality for each edge. And as we've argued, that goes all the way back to proving the theorem. Okay? Question? How do you figure?
It just looks that way. I mean, maybe.
So the left-hand side is the pink rectangle, and the right-hand side is the green rectangle.
Wait, the whole thing?
Yep, whole thing.
So like including the area in pink?
Oh yeah.
Oh, okay. Well, then never mind.
Yep.
Where do we actually use our equation for what the cost of the network is? Was that never used?
Where do we use our equation?
What the cost function of what the routing looks like? So like the 1 over x or whatever?
Oh, we don't. Yeah, so if you look at the theorem statement, maybe I should have made this more clear. Yeah, let me make this more clear. So you're absolutely right. All that this theorem needs is continuity, non-negativity, and non-decreasing, and that's it. Now the reason, okay, so just to remind you of the interpretations I gave you before this proof, you might be thinking, okay, it's kind of, isn't this apples and oranges? Like, isn't it sort of weird to compare, like, one net, why does optimal have twice as much traffic? What does that mean? Okay, so this is the formulation in which the proof is the nicest. So I proved this version of it. But on the exercise, I ask you to do a change of variable to observe that a totally equivalent statement to this theorem is to look at two different flows with exactly the same rate. But when you route optimally, you have a slower network in a precise sense. Okay, that'll be spelled out in the exercise. So again, you have optimal, you have equilibria, but rather than twice as much traffic, you have slower network, okay, and same traffic. And then if you take that statement and you take the cost functions to be these MM1 cost functions, 1 over u minus x, then it's a particularly nice interpretation. The change of variable has a particularly nice form. It really says that if you do equilibrium routing after doubling the capacity, that's only better than optimal routing in the original network with the original capacities. Okay. But it's only that, one, I mean, if you have an arbitrary cost function, doubling the capacity is not defined. So with the MM1 cost functions, there's a notion of capacity on the edges, so I can make a statement about doubling the capacity. But the basic comparison holds for any cost functions. Yep? Where what? Continuity comes into existence of equilibria, which is a fact I stated on Monday. Yeah. Okay. Any other questions? Cool. So on problem set 1, one of the questions I asked was to, in the spirit of the poor incentives in the badminton tournament in the 2012 Olympics, I asked you to go find other examples out there in the real world of systems where the incentives were not quite right. So a couple of you came up with pretty nice examples. So I'll just tell you one now. Probably I'll tell you one or two others in later lectures. But one team of students pointed out that there's I hadn't heard of this actually. I'd heard of spelling bees, of course, but I didn't know there was, I'm not surprised, but I'd never heard of the National Geography bee. But there is one. Maybe some of you are alumni, I'm not sure. My understanding is it's for 6th, 7th, and 8th graders. And the way the rules of the competition are is, so they rank the top, 15 or what have you. And, there's various cash prizes. $25K for first place. I don't know what you do with $25K as a 6th grader. I guess probably your parents just put it in your college tuition account. That's about the end of it. But anyway, so they rank you, and there are these cash prizes. And, of course, it's tons of glory, if you place first in the geography bee. So the rules are, so again, it's 6th, 7th, and 8th grade. And the rules are if you place first, second, or third, you cannot enter again. So if you're an 8th grader, you want to do your best. But if you're a 6th or a 7th grader, and you're not going to get first, maybe you don't want to get second or third. Maybe you want to get 4th. Right, so you can enter again the next year. Because hey, if you get 4th as a 6th or 7th grader, your chances look good as an 8th grader, right? And so it's unclear if there's actually been people intentionally using the strategy. My guess is it would actually be pretty hard to pull off, to just sort of, be hard. If you're shooting for 4th, you might get 3rd instead. But it has been acknowledged that so one winner as an 8th grader was in fact 4th place as a 7th grader, and actually commented in an interview with Alex Trebek that the previous year he was really hoping he'd get either 1st or 4th, and so he did make that comment. So it's not lost on the very smart contestants. Okay, so a little bit more about routing. So I want to relax one of the assumptions we've been making thus far. We've been thinking about, very small agents, cars on a highway, individual packets in a data network. And so it made sense to model the population as basically being a continuum, basically there being an infinite number of players. Some contexts you don't want to do that, like if you're modeling an entire internet service provider routing its traffic, that is not a non-negligible agent in a network. So I want to look at a finite number of agents that are of non-negligible size. So in addition to being a natural model, we're going to get some new kind of phenomena that's going to show up in the next couple of lectures as well. Okay, so this will give you a gentle introduction to some of the complicated things that can happen in other important models. All right. So the deal now is there's a finite number of players, k, and each with its own source and sink. They might all be the same, they might not. Okay? Sink TI. And I'm going to keep things simple. I'm just going to assume each has exactly one unit of traffic to send. Okay? And the responsibility of a player is to pick exactly one path from SI to TI. Okay, so it's going to have this one unit of traffic, and all of it gets routed on an SI-TI path of the player's choice. The objective function of a player is the same as before. It just wants a path that has cost as small as possible. And as usual, there were these edge cost functions. So short cost is with respect to the current traffic pattern. Okay? All right, so let's look at an example. It's a slight variant on Pigu's original example. So rather than tons of agents, there's only going to be 2. Okay? And I'm going to change the 1 to a 2. Okay? The top cost function is still the identity function. Okay? So on the bottom, any player using the bottom link has cost 2. It doesn't matter if both of them are there or just one of them. If there's one player on the top link, the cost is 1. If both players are on the top link, the cost for each of them is 2. Okay? So the objective function is going to be the same as before, just this total cost of all the players. So what seems like the optimal thing to do? Is that easy to see? Well, for an optimal solution, there's no reason to randomize. There's just going to be one solution that's best. For equilibria, it's going to be relevant, but for today, we're not going to allow randomization. But it's a good question for equilibria, but for today, no. So you want to split them on the 2. Okay? So you want to do one player on each for the cost of 3. Okay, whoever gets stuck on the bottom has cost 2. The person on top is lucky and has cost 1. And this is an equilibrium. So what do I mean by an equilibrium? I just mean it's a traffic pattern where if any player unilaterally switches its path, meaning the other k-1 players stay fixed, then any path switch only makes you worse. Okay? Your cost either stays the same or goes up. It can't go down. If there's a player who can switch a path and get less cost, then it's not an equilibrium. Okay? So this I claim is an equilibrium. Certainly, it's obvious for the top player who has cost 1. They're very happy to have cost 1, don't want to switch to the bottom. But what's a little interesting, and now already a little bit different than the previous model, is this player on top, even though they're sort of bummed out, they have cost 2, and they're jealous of the other player who has cost 1, there's nothing they can do about it. Right, so if the player on the bottom switches to join the player on top, what's its cost going to be? It's again going to be 2. So just because it looks upstairs and sees a player with cost 1 doesn't mean it can join it and also enjoy that cost of 1. And that's different. Okay? When you were negligible, you could switch paths and enjoy whatever costs they were already incurring. Okay? So this is an equilibrium. You see another equilibrium? Both on top. That's right. Because again, you have cost 2, you switch, you can't help it. Doesn't matter. Okay, your cost doesn't go down if you switch. So what's the cost of this equilibrium? It's worse, actually. Right? So this one has cost 4. So this is an important point. This did not happen in the previous model. I didn't prove it, but I asked on Monday for you to take it on faith that all equilibria have the same cost in the nonatomic self-shrouding model. Here, and in fact in most games, you can have multiple equilibria which have different objective function values. All right? Right, so the definition I gave you of the price of anarchy on Monday is now obsolete. Okay, what I wrote was cost of an equilibrium in the numerator and cost of an optimal on the bottom. The bottom still makes sense. There's still an optimal solution. It's not well defined to just write cost of an equilibrium because there's many and they don't all have the same cost. So we have to make a choice, okay, about which equilibria we want to talk about. The best case scenario, as far as proving upper bounds, of course, would be to give a bound on every single one of the equilibria. Okay? That's what we'd love to have for positive results. And for today, that's what we're going to do. We'll talk about other choices later on. So redefinition of the price of anarchy. On the numerator, if there's many equilibria, we take the worst of them. Okay, so in this one, we would take the second equilibrium over the cost of opt. So e.g. equals 4/3 in the example. Okay. Questions? So that's the first big technical difference that happens when you relax the assumption that players are small and you allow them to have non-negligible size. So I'm next going to state a fact. If there's time at the end of the lecture, I'll actually give you the details, but let me just state it for now, which is another difference. So this is example 18.6 in the AGT book. So they're less well behaved not only in that you can have multiple equilibria, but they're also less well behaved in that the worst of these equilibria can be worse, i.e. less close to optimal, than the bounds that we just proved in the nonatomic case. So if you restrict to, say, affine cost functions, ax plus b, we proved on Monday that the price of anarchy is always 4/3 or better in the nonatomic selfish routing world. Here it can be bigger than 4/3. It can be as high as 2.5, 5/2. Okay, so not a total disaster, but noticeably larger than we had for the case of negligible sized players. Okay? Yeah?
Is this independent of the number of players we have?
Yeah, so this is a lower bound. So this is just some concrete example. And so the example in the book uses 4 players. On the exercise set, I ask you to come up with an example with 3 players. The upper bound I'm about to give you will be for any number of players, which is what you'd want. So, right. So the main other result I want to tell you about today is a matching upper bound. So this was proven independently by 2 groups, Auerbach-Azar and Epstein, and Christodoulou and Koutsoupis, mid-last decade, which was that there is no example worse than this for atomic selfish routing networks. 2.5 is in fact tight. And so this is for any number of players, any number of sources and destinations, arbitrarily large network size. Okay, so that's the bad news is the constant is not quite as close to 1 as before, but the good news is qualitatively this still tells us something extremely non-trivial. It says you can scale up your networks as much as you want, and the price of anarchy does not grow with the network size or the population size. It remains bounded above by a universal constant. Any questions about that theorem? Okay. So there's a couple of reasons I want to show you a full proof of this theorem. I mean, it's not that long. One is, it's just a basic result in the area of routing games, but also this proof will have a particularly canonical flavor of how you prove upper bounds on the price of anarchy. And it's even canonical in a sense that can be usefully formalized, which we'll develop next week. Okay, so this, in the future, will be sort of a canonical example of some more general method for proving these price of anarchy bounds. But for now, let's just understand why this theorem is true. So the usual notation, F is an equilibrium flow. There might be many, but this proof will work for any of them, and therefore will give us a price of anarchy bound. So F is an arbitrary equilibrium flow. F star is the optimal flow, the one that minimizes the total travel time. And each cost function is affine. So of the form AEX, or AEX plus BE. Okay? So I'm going to be using the same notation we were using before. So like F sub E will denote the total amount of traffic that uses an edge E. If you think about it, we just have these K players and each picks one path for one unit of traffic. So F sub E will just mean the number of players that choose a path that includes this edge E. Okay, that's going to be the total load of the edge. So we'll write FE for number of players using E in their path. You know, same thing for f star e. So that's the number of players that, in the optimal solution, that use a given edge e. All right, so 3 steps. And all of these steps are sort of canonical in a sense. So how are we going to do this? So what do we need to prove? We need to prove the price of energy is at most 5 halves. What does that mean? That means that the cost of this equilibrium flow is at most 5 halves times the cost of the optimal flow. So we need an upper bound on how costly the equilibrium is. Okay? So, all right, what do we have going for us? Well, so affine cost functions, we got to use that. But also, we better use the fact that f is an equilibrium, right? That should be clear too. If f was just any old flow, an arbitrarily stupid flow, we're not going to be able to prove anything about it. So it's important it's an equilibrium. So we need a plan for somehow using that hypothesis in our argument, right? How do we use that f is an equilibrium? All right, well, let's remember what it means to be an equilibrium. It means that if any player switches paths, they only get worse. Okay? That's the definition of an equilibrium. So that's cool. That means if we pick a player and we pick a hypothetical deviation, we say the cost would then only go up. So that actually gives us an upper bound on the player i's cost in an equilibrium. Right? It would only be worse if it switched. Okay, so that's an upper bound on the equilibrium cost. And that's good, because we want to upper bound the cost of the equilibrium, of everybody, not just of a given player, but of everybody. So what seems like a good idea, what seems like kind of the only way we might use the equilibrium hypothesis is to say, well, pick a player I, pick a hypothetical strategy, and it only gets worse. And that'll give us an inequality. Okay? So we just have to think about, okay, so what path might we sort of hypothesize I switching to? And somehow, probably the most natural choice is just to say, you know, why isn't this player I doing what I wish it was doing in the optimal solution? Okay? If all the players did that, you know, we'd be fully optimal. And somehow it's not. So I kind of want an explanation for why player I is picking its equilibrium path and not its optimal path. Okay? And the reason it's an equilibrium. Okay? But that'll give us the first inequality. All right. So precisely, using the equilibrium hypothesis, since f is an equilibrium, no player I wants to switch. I'm going to use the notation pi. So this is the path that player I uses in the equilibrium flow f, and p star I is what we wish it was using, its path in the optimal solution. Okay, so i's opt path. So that's the notation pi and p star I. Okay? And by doesn't want to switch means its cost would only go up. i.e., sorry. So if I look at the cost of player I in the equilibrium, right? So the cost of its path is pi in the equilibrium. So this, remember, is just the sum over the edges in the path of the edge costs. So this is how well player I is doing right now in the equilibrium. If it switched, it would only get worse. Okay? So what would be the cost if it switched? Well, so what's the picture? Right, so we have this network. We have SI, we have TI. It's doing something in the equilibrium. All the other players are picking their paths in the equilibrium. And, you know, P star I looks like something else. Right, it's some other path. You know, they may share some edges, but it's some other path. Okay? So if player I deviated from pi to P star I, there's kind of like 2 kinds of edges. Okay, there are the edges that are in both of the paths. Right? Maybe they have the same prefix, for example. So it's going to pay exactly the same cost as before. But then there are going to be these edges which it sort of newly uses, okay, which are in the new path and not in the old path. Okay? So the cost, if it switches, well, there's all the there's the business as usual in the edges it was already using. And then in the edges which are in the new path but not the old one, what do I need to write here? Right. In the equilibrium F, there were, like, say, 5 players using it. And now this player deviates, it becomes the 6th. Okay, that was the same reasoning we used up here for why, when the players are split, there's actually no incentive for the bottom player to move to the top, because then it actually adds its own +1 once it moves. Okay? So this is exactly its cost in the equilibrium. This is exactly its cost if it switches. And this inequality is because we assume F is an equilibrium. Okay? Any questions about that? I'm fixing an optimal solution, and I don't care which optimal solution you fix. So in the same way, I don't care what equilibrium you pick. I don't care what optimal solution you pick. They all have the same cost. Yep. So for the paths that are in common between pi and p star I, it's the business as usual, same cost. And then for the edges which are in p star I but not in pi, it's the cost of f sub e plus 1, because I has joined them. Huh? Why is or is not? Okay. So, well, you know, we're doing an upper bound, and for all we know, pi and p star I are disjoint. Okay? For all we know, there's no shared edges. So let's just keep things simple and write this. Its equilibrium path cost is bounded above by the sum over the edges in the optimal path p star I, where we always add 1 to take into account i's possible new presence. Okay? Good. So that's step 1, already done. Okay? So step 2, all right, so this is good. We've used the equilibrium hypothesis. For each player I, we now have an upper bound on how costly it is in the equilibrium. All right, and that's going in the right direction. Okay, the price of anarchy demands a bound on the overall cost of the equilibrium, okay, with respect to the optimal. So step 2, let's sum these up. So we have one inequality for each of the k players. Okay. So what do we get? Well, for the left-hand side, all right, so left-hand side, we sum over the players, I equal 1 to k, sum over the cost and their edges. Okay? So I want to do the same. Okay, I just want to simplify this. So how many times? So pick your favorite edge, edge number 17. Okay. So how many times does the cost of edge number 17 appear in this double sum? Well, it appears once for each player I, for which edge E is a part of its path. Okay. So if 3 different players have a path that includes edge number 17, then the cost of edge number 17 is going to show up 3 times. Right? So this is just the sum over all of the edges of the corresponding cost of the edge multiplied by the number of players that actually pick a path that use that edge. Okay? So this is the left-hand side after we do the summing. So right-hand side after summing is, let's see, what's this thing? So sum over I equal 1 to k, sum over E and P star I, C of FE plus 1. Same reasoning, how many times does for a given edge, edge number 18, how many times does this term show up? Once for each player who uses that edge in its optimal path P star I, also known as F star I. Okay? So this is just equal to sum over all the edges, F star E, CE, FE plus 1. Okay? So again, what I did is I took this, which held for each player I added them up and simplified. Let me simplify the right-hand side a little bit more. Everything I've done so far has been for any non-decreasing cost functions. I haven't used the fact that they're affine. So let's now expand this, knowing that the cost function CE is of the form AEX plus BE. this is just substituting. Okay, that's just multiplying out. All right. So that's the end of step 2. Let's take stock. All right, so what do? We summed up these inequalities. Why did I do that? The reason I summed up all these inequalities is because the left-hand side is something I care about dearly. Right? This is just the cost of the equilibrium flow. All right? I had this set of inequalities. Inequality I just upper bound the cost of player I, so I add them all up, I get an upper bound on the cost of everybody. And that's the whole point of this theorem. So the left-hand side, I get something I care about. The right-hand side, I then just kind of saw what I got. And I actually got something I don't care about at all, really. So like the semantics of this term are totally unclear, right? Like what is FE times F star E? The number of players in the equilibrium times the number of players in the optimal solution. It's like some weird entangled version of these two different things, okay? So I don't know what to make of this, right? This just is what it is. So step 3 then says, well, okay, I don't care about this. The only two things I actually care about are the cost of the equilibrium and the cost of the optimal flow, right? That's what the theorem's about. Okay, eyes on the prize. Right? Those are the two things we care about. So step 3 has to basically just relate this back to the two things we care about, the equilibrium and optimal costs. All right? Okay. So step 3. We'll begin with an exercise, which is an inequality whose responsibility is to basically disentangle this confusing product of f and f star. F by itself, we kind of know what to do with. F star by itself, we know what to do with. The product, we don't know what to do with. So we have this inequality which says, consider any non-negative numbers, integers, y and z. It's the case that the product of y and z plus 1. All right, so this is an entangled version of something. And here's the disentangled version of it. 5/3 y squared plus 1/3 z squared. All right, so we'll put this to use in a second, but first let's just stare at this. So what if I choose y equals z equals 1? What are both sides? Both sides are 2, right? Okay, so it's tight if y equals z equals 1. What if y equals, let's see, what about y equals 1 and z equals 2? What are both sides if y equals 1 and z equals 2? Both sides are 3, okay? Okay, so it's tight for those two cases. The claim is it holds, in fact, strictly for any other combination, okay? Once someone's pulled this out of a hat and asked you to verify it, it's really not hard, okay? You just brute force check these small cases, a few small cases, then it's clear it holds for larger values of y and z, okay? But I'll leave that for you. The question of like how on earth would you come up with this in the first place, that'll actually be a little less mysterious, in about a week or so in the course, okay? I mean, already once we put it to use, it'll be a little less mysterious, okay? So this is true. And again, the role of this is to disentangle a product into individual sums. And so the way we're going to apply this, right, so this was this entangled version of equilibrium and optimal flows that was puzzling us. So this is going to be our y, and this is going to be our z. Okay, or y sub b and z sub b if you like. We're going to apply this inequality once for each of the edges of the network. Okay. So, all right, so remember the left-hand side, we had the cost of f. That was this left board. And then the right-hand side after summing was everything here culminating in that thing on top, to which we will now apply this inequality once for each edge. Well, on a given edge, f star e playing the role of y and fe playing the role of z. So what do we get? All right. So we get is the f star e times fe plus 1 becomes a 5/3 f star e squared plus 1/3 fe squared plus be times f star e. Yeah. So now let's be sloppy in the interest of simplification. So let's collect all the f star stuff. So just for kicks, I'm going to just multiply that by 5/3. Can only get bigger. And that lets me bring the 5/3 out, sum over e, and now the f star e terms look like this. And then the remaining fe terms are this. So this has another name. What is that? That's just the cost of f star. Okay, so remember this by our affine cost functions. This is just the cost of the edge for f star. Okay, so that's just the sum over e of f star e c of f star e. So at most 5/3 times cost of f star. What about that? Yeah, this is at most the cost of f, right? If just for kicks, I threw in a bunch of b sub e's here, sorry, b sub e, f sub e's, which would only make it bigger, then this would be exactly the cost of f. Okay, so that's upper bounded by the cost of f. Cool. So this little inequality allowed us to disentangle the right-hand side that we didn't understand in terms of a linear combination of two things we care about, the cost of the optimal flow and the cost of the equilibrium flow. So remember what the left-hand side is. The left-hand side is the cost of the equilibrium flow. So that appears on both sides. On the left with coefficient 1, over here with coefficient 1/3, happily less than 1. So we subtract this from both sides. That gives us a 2/3 cost of equilibrium on the left. We multiply through by 3/2, we get what we want. So we get that the cost of the equilibrium is at most cost of opt times, we have the 5/3 to start with. And again, we subtract the 1/3, it gives us the 2/3, multiply back through, times 3/2, which is our 2.5. So that's that. Questions? Was the Yeah, I'm actually going to show you that now. It only takes a couple minutes. I've got a couple minutes. So, yeah. So I'm going to show you that there's no better bound possible. That in fact, 2.5 is the right answer, despite the fact that maybe this inequality felt ad hoc. It's actually given us the best possible bound. What are the questions about the upper bound first?
I'm not quite sure I get the correlation between the second term of both the right-hand sides. Like the 1/3 sum and 1/3 cost of that.
Here? Yeah, so this is exactly the cost of f star. So it's an equality for this. So if I could make this bigger, by throwing in a sum over E of BEFE. And then that would be exactly 1/3 the cost of the equilibrium. So this is something bounded above by 1/3 of the cost of the equilibrium. It's just missing the B terms. Yep.
Is that if you increase the traffic to a very large number so that each traffic load, each individual is very small compared to the total? So should that approach the problem we mentioned previously?
Good question, right. So what you'd hope would be true is that under some natural limit, this atomic model would basically become the non-atomic model. And the answer is yes. Basically, what you'd want to be true is indeed true.
So that bound is not tight.
I mean, so this is tight for worst case atomic selfish routing networks. I mean, I'll give you the example right now where it's tight. But if you then make additional assumptions, then of course it need not be tight. So if you assume that there's a bazillion players all of cost epsilon while keeping the cost functions normalized, then no, it's not going to be tight because it will approach the other model. Other questions? Okay. So here's why it's a tight example. So it's a bidirected triangle is what it is. Yeah. So there's 6 edges. 2 of them are zeros, 4 of them are x. Okay? There's going to be 4 players, each with 1 unit of flow, and the 4 players will be in 1-to-1 correspondence with the 4 edges that are labeled x. Okay? So for example, here's an edge that's x, and here's a player number 1, S1T1. The obvious thing for player 1 to do is just take its 1-hop path of cost x. Okay? And there's going to be 4 analogous such players. Okay, so that's the example. Like in that first example I showed you with the x and the 2, the optimal solution will also be in equilibrium, but then there'll be a second, in this case, considerably worse equilibrium. Okay? So the obvious routing so I guess the first thing to notice is it's a bidirected triangle. So as a player, you have 2 paths. The obvious path is to take 1 hop and go straight to your destination. The alternative way is 2 hops around the other triangle, okay, around the other side of the triangle. Right, so for example, S1, either you can do the obvious 1-hop path, or for some reason it could go via a 2-hop path. Okay, and all 4 players have that thing. Yeah.
Are we allowed in our model to put directions on edges? So any player should be able to take.
Yeah, it's been a directed graphs all along. Yeah, we've never used undirected graphs. A model we'll talk about Monday, it'll matter. But for these routing networks, it just doesn't matter, it turns out. Yeah. Okay, so ops. So all players on 1-hop paths. And then the cost equals 4. Okay? Because there's 4 x's, each one has population 1, so it's a cost of 4. That's also in equilibrium. There are 2 zero edges, but the 0 edges are not in correspondence with anybody's source directly, source destination pair, so no one has a 0 path available, so cost of the 1 is the best you can do. So if all players simultaneously get cost 1, it's going to be in equilibrium. You can't do better. Okay? But if all of them pick their 2-hop paths, and I know this sounds crazy, but check out what happens. I've tried doing this where I actually draw the 2-hop paths, but it gets kind of messy. So let's do instead the following. On each edge, I'm going to keep a tally of how many players are using that edge as we go through the players one at a time. Okay? So S1, instead of going there, is going to go there and go there. Okay? And please watch me carefully. This is very easy to make mistakes in this demonstration. So if S1 takes its 2-hop path, that puts a first player on this one, and then it puts a first player on this link as well. Okay. So let's do the same thing. So S2, there's T2. So that's its 2-hop path. So that'll put 1 there and 1 there. S3, there's T3. So that'll go this way. So that'll put 1 on this 0, and then a second one on that X. And S4, there's T4. So there's the 2-hop one there. So that's a 1 on that 0 and a second one on that X. Okay. So the orange tick marks are denoting the edge loads. Okay, look good? So I claim that everybody simultaneously foolishly picking 2-hop paths is actually in equilibrium. Nobody can do better by switching back to their 1-hop path because the other 3 people are too busy flooding the network. Okay? So for example, consider player 1. Okay, so player 1 is one of the ones that's worse off. Okay, so notice here that 2 players have cost, what is it? I'm not so sure about that yet. Okay, but let's consider player 1. Okay, so currently player 1 is incurring cost 2 plus 3. Right? So player 1 seems to be like, it's got to have a way to do better. Right? But if player 1 switches from its 2-hop path to its 1-hop path, it becomes the 3rd player on that edge. So its cost will remain 3. Okay? And you can do the same observation for the other 3 players as well. So because all the other players are busy flooding the network, you actually can't go back to your 1-hop path and be better off. So 2 of the players are like, so player 1 and a second player have cost 3, and then 2 of the players have cost 2, so that gives us a total of 10. So that gives us a price of anarchy of 2.5. Okay. Any questions about that? So coming up next, we'll look at a variant of these routing games where you have positive externalities, and that's somewhere where we'll have a multiplicity of equilibria, some of which we really don't want to argue about. So we'll be looking at alternatives to the price of anarchy concept in the presence of multiple equilibria on Monday. Have a great weekend.